Hello, everyone. My name is Livnat Pierre. I'm a senior engineering manager here at Red Hat, Israel. I'm here also representing Superfluidity, which is a research project supported by the European Union focused on 5G networks. And it's one of the contributors for the use cases of quality of service we're going to discuss. So here we go. We've been talking in the community about networking quality of service for the past 3 years. The first 2 years, not a single line of code was merged into the database, or into the Git, actually. The reason for that is that basically we were having an ongoing discussions with multiple vendors, and we were trying to get to a common API where everybody agrees on something. And that was stupid, to be honest. Like, it didn't work. We knew it at the time. There were multiple work-in-progress patches being sent into the repository. None of them hold. So a year ago, we've decided to take a bit of a different approach, right? We said, OK, obviously there's not a common standard in the industry to measure quality of service. There's no one way to say, OK, we are using throughput, or we want to test or to measure latency, and there's a way to do it. So what we've decided is, instead of boiling the ocean, we would focus on a very concrete, very specific, simple to solve use case. And that's the noisy neighbor problem. For those of you who are not familiar with it, the concept is that you have a shared resource and multiple consumers. And the thing is that you want to make sure that none of the consumers is taking more than its fair share of the resource. In our case, the resource is the bandwidth in the compute, and the consumers are the virtual machines who are using this bandwidth. So we want to make sure that we do not have any one virtual machine who's being very chatty and overtaking all the bandwidth. So this is the problem we've decided to tackle, and obviously it seems like a well-defined problem. It was much easier to start the discussion and to actually get things done. At least that's what we were hoping. So what we did a year ago is that we had a code sprint in Tel Aviv in the Red Hat office. We got participation from 5 different companies across the world. We got people joining from remote and actually contributing to the discussion and patches that were merged into the code base. So in these 3 days, we were focusing on 2 things. A, let's solve the noisy neighbor problem. B, let's make sure we are putting in place a generic framework that would easily be extendable later on to accommodate the million other use cases that were mentioned. So with 2 things in mind, we started coding and came up with something which is very basic, simple. There's the quality of service policy that was introduced. Each policy is a container of multiple rules, and it can be applied on a port, on a virtual machine port, and that means the policy is applied on each traffic that goes in and out from that port, or you can choose to apply it on the network. If you choose to apply a policy, a quality of service policy on the network, by default it means that each new port that is being created on that network is going to inherit this policy. Very simple concepts, at least that's what we were hoping to get. And maybe one delicate thing, if you obviously have a policy on the network and a policy on the port, the later one holds. So the more specific policy holds. And that's what we started with. From the user perspective, a quick overview. So it's as simple as creating a policy of service in the Neutron CLI. You give it a description and a name. Then you create a concrete rule within the policy. There are different types of rules. We're going to go over them. But in this specific example, I chose the quality of service bandwidth limit rule. There are 2 parameters you can define there and within a specific policy. Once the rule is created, you can choose if you want to apply it with a port update on a port or with a net update on the network. Hopefully very simple. Okay, all of this was introduced in Liberty. Obviously, to solve the noisy problem, noisy neighbor problem, we had to implement one rule at least. Like there was the abstract entity that was added into the code base, but also the specific bandwidth limit rule which was added. And until this point, we're talking API level, something that everyone, each Neutron driver can implement. In the Liberty cycle, we were focusing on two implementations. The first is obviously the reference implementation, the OVS-based one. And we also implemented it in the SRIOV driver. So we have support for quality of service for this specific rule, the bandwidth limit rule, in Liberty. Then in Mitaka, there's a group of people who added the support for Linux Bridge. And I know that they are working in OVN now to do the same thing. So it's expanding, and it's nice to see how the community is actually adopting this API and extending it. So this is one type of rule. And then we got the second contribution of a new type of rule that is actually the first feature that was merged in the Neutron cycle, the cycle that we're currently developing in upstream. And that's the DSCP marking rule. The DSCP marking rule is basically about tagging traffic that leaves the virtual machine. We have a concrete use case by Comcast that are using this marking to classify specific types of traffic and then prioritizing it based on the marking. So this is the second type of rule, and obviously we're hoping to get more contribution as we go on. To make sure we are not confused, then per version you can just type which versions are supported, like which versions, which rule types, are available, and you get the list of the available types that are supported within the version. I think it's very useful for users to know what's going on. One interesting concept that is worth mentioning, I think, is how we chose to implement the propagation of a policy. So we chose that once you apply a policy on a port or on a network, the changes would immediately go to the VM that is running with that port, so with no downtime. To support that, we had to implement two different use cases. So the first is if you attach a new policy to a port. So if you had a port, it didn't have any policy, it's a new feature, great, you want to use it. You want to associate a new policy with that port. That's one thing. The same flow exactly applies when you take one policy and change it with another policy. It's the same thing. So this is, in high level, the mechanism that we're using. You can see on the left-hand side the Neutron server. On the right-hand side is the L2 agent who's running on the compute node. When there's a change to the port, because there's a link from the port to the policy ID, then you get a notification to the bus. The port update notification is being picked up by the agent. You ask for the port details. If the port details have reference to a new policy ID, the QA agent extension is basically asking for more information about the policy and updates the data live. So that's how you basically are able to apply new policy on a VM with no downtime, which is nice. The second scenario is that you already have a policy, you don't want to change it, you just want to update the parameters within it. For example, you want to increase the bandwidth that you allocated. So for that, we use a basic published subscriber model. You have the agent register for updates on the policy. On the Neutron server, the plugin basically publishes any new data that is, or any new change that is happening in the policy. It's being picked up by the agents, and that's how, again, we get it live while the changes are happening to the policy. Okay, one more thing that we did in that we did in, well, it's not really in Liberty, it's in Mitaka. So in Liberty, the mechanism of role-based access control was introduced into the code base. The idea behind role-based access control is that you have fine-grained control on the permissions for an entity. So for example, if you have a network, and before the RBAC mechanism was introduced, you could only say that a network is either public, meaning all tenants can view it, or private, only the owner of the network can see it. Now you can choose. You can create a network and choose which tenants exactly can view and use that network. So this is a mechanism that was generally introduced in Liberty. And the question was, how can we adopt it in the quality of service? So in the Liberty originally, where we added support in quality of service, we said, OK, there's no mechanism in place yet. We have to support all or nothing, similar to what we had with networks. So we could have private quality of service policy or public ones. And by default, only the cloud administrator could create the policy, the quality of service policy, and associate it with the networks. And once we have the RBAC mechanism in place, we added support in Mitaka to actually extend it from network to quality of service policy. So now you can basically create a policy and choose which tenants have accessibility to that quality of service. So you can share it in between the tenants. And we found it something that the operators like. So that was nice. We got a good feedback on that feature. OK, so what's next? And that's where I want to actually focus in the discussion today. One of the things that we were hoping to get and we were working on from day one is the minimum bandwidth guarantee. That was like the #1 feature that was asked by operators, by users, by Red Hat customers, by anyone who's using this thing. Basically, OK, we need to guarantee some kind of service agreement to our customers. How do we do that? Looking at the API, it's as simple as adding a new parameter in the bandwidth limit rule. You guarantee a minimum of something in kilobits per second, and that's it. Like, the API seems easy. So we were looking at it, and that's where the actual challenges came. So one thing which is not really a challenge, it's more of a, well, it is a challenge. You have to get into agreement with the community. You have to discuss how to implement it. So one of the first things is basically how friendly we are, or it's also known as borrowing. The concept behind it, and this is something we need to agree on, is when a VM is guaranteed a specific minimum bandwidth and is being deployed on a hypervisor, but is not really using it, can we borrow it, the bandwidth, for another virtual machine to use at the same time? Well, apparently, there are different opinions in that domain. Some people or some users say, if we guaranteed it, then we need to make sure it's available at all time, even though we are paying the price of not utilizing our hardware to the best that we can. So this is one approach. The other approach is, if the virtual machine is not using it, we can use it for something else. Like, let's focus about utilizing the hardware. Both solutions are fine. Like you can take either approach. We just need to get to an agreement and actually implement that. So that's the easy part. The more challenging part is the second thing. So when we want to implement minimum bandwidth guarantee, one of the biggest challenges is that we need to integrate with the Nova scheduler. We need to have some kind of collaboration with the VM placement algorithm. Let's try to see why. So if we have 2 compute nodes, each one of them is 10 gig, has 10 gig throughput, and we want to schedule a virtual machine which, with a minimum bandwidth guarantee of 7 gigs. We can choose wherever we want, right? Let's assume we choose the first compute node. And then there's the second compute node that requires 5 gigs as a minimum bandwidth guarantee. That's where we need to make sure the Nova scheduler is aware of all of it and make sure that it's being scheduled on the second compute node. So it's obvious why we need to collaborate with Nova scheduler. The question is how we do that. We've been working with the Nova community for 2 cycles at least on this specific, because as I said, it was #1 feature in quality of service that was asked, and still being, people or users are still looking for to see it. But we were a bit unlucky because the quality, the Nova scheduler has been going through a massive refactoring in the past 2 cycles. And that requires some explanations because it actually blocked this feature from us to be able to implement the feature. So the way Nova Scheduler works today is that it has different types of resources, and per resource, the counting or the inventory is done in a unique way. So if you want to count CPU, or if you want to count memory, or if you want to count anything else like physical requirement, for example, an SRIOV card or anything, each one of the requirements is implemented differently. And the Nova community rightfully said that it doesn't scale. You can't choose a different way to implement it per resource. So they were into introducing a new mechanism that would enable us to do it in a homogeneous way. And for each resource, to have the same approach and be able to count it in the same way. So this is the mechanism. I'll go over it quickly. The mechanism they introduced, and that is still being under development. So the first thing is they introduced the concept of a resource classes. A resource class is, in our case, would be the throughput, for example. If you're talking about storage, it would be the storage. It can be the CPUs. It can be multiple different things. So we have a resource class. That's the resource provider. In our case, whoever provides this resource is the compute, right? So we have a throughput, and we have the resource provider. We have the throughput and the resource provider, who's the compute. And then there's the compute node inventory. We need to count how much throughput is there to start with, how much is being used, and how much is still available. So this is the third type of class. And the fourth one is the resource provider allocation. That's the smart part where you actually do the correlation between the API call that requires specific kind of quality of service, and you associate it with the inventory, like which one of the compute nodes has enough of the resource I'm looking for. So this has been going on for 2 cycles, as I mentioned, and it's still not there, so we can't count on it. What we can do, and this is what we've been doing, is split the minimum bandwidth guarantee into 2. There are 2 parts. The first part is being able to place the virtual machine on the right compute node. That's the part where we kind of block. The second part is assuming the virtual machine is already in the compute node, we still need to actually guarantee the throughput. And this part is independent of Nova. We can accommodate any kind of solution within Neutron, and this is what we've decided to do. We're going to solve that problem in the Neutron cycle, hopefully, and focusing on what we called best effort minimum bandwidth guarantee. The idea is we do not have any control at this point on the placement. We will, hopefully in the next cycle, but we do have control that once the virtual machine is scheduled and being run on a specific compute, to actually allocate, if possible, the minimum bandwidth guarantee that is committed in the policy. So from our perspective, we are doing the best. Our is the Neutron perspective. We're trying to do the best we can in that context, but there are multiple things that are going on. And this is one of the challenges that we face as a community to collaborate in between projects. OK, another cool feature that we're working on is the traffic classifier. A traffic classifier is needed to identify specific types of traffic. So for example, the HTTP traffic, or the SSH traffic, or VoIP, or whatever. So the idea behind this is that once you classify a specific type of traffic, you can apply different rules on that traffic. And that was something that we started to work on in Mitaka, and we're still working on it. The challenge with this specific feature, is that it's a great feature. It's needed by multiple things in Neutron. And not only in Neutron, also there's the project that is a service function chaining project. They had the same requirement exactly, and they implemented traffic classifiers within their solution. So our challenge is how can we develop that feature without having two code paths or two implementations of the same requirements. So again, what we're doing here is we're working in collaboration with the SFC project to find what we call a shared, or define a shared library that can be used by both projects, hopefully maybe more than just a library, but library is like the basic thing that we have to share. And then based on a shared library, we would be able to utilize it within quality of service. It's not only quality of service in SFC, there's also security group that are looking to use in traffic classifiers. So we think that this is a key feature that would be used all across the Neutron API. So here I put the kind of one of the optional models that we have to a policy. This is one of the options that we're currently discussing, but it could change. And if you guys have better ideas, then we'd love to get them. So a policy has multiple rules, and each rule would be we would be able to associate a traffic classifier with it. And then the rule would only be applied on this specific type of traffic. Okay, additional future work. Well, we have plenty of things that we've been discussing, but there's only so much we can do within one cycle. So one of the easy things that can be done, and again, that is a feedback that we got from operators, and that's having a default quality of service policy per tenant. So when I create a tenant, I can say, okay, each VM or each port in that tenant would be limited to 1 gigs by default of throughput, and then this would be the default policy for all the ports for that tenant. So this is the feedback we got from operators, and we think it's an easy implementation, so we might be able to do that in Neutron. And another thing that we are working on is the shaping of incoming traffic. So to sort out the noisy neighbor problem, all we had to deal with is traffic that is leaving the virtual machine. We were able to apply policies that are applying on the traffic that is leaving the VM, and this is it. The problem is solved. The challenge is that we now need to deal also with traffic that is incoming into the virtual machine. To be honest, in the OVS itself, it's not so complicated, so we will be able to do it, again, hopefully within the Neutron cycle. For other implementations like SRIOV, it seems like it's not an option to implement it. So there will be only partial implementation available going forward for this specific feature. In addition, we have many other things that we're discussing, and it's really nice. You can go ahead, there's a link there. Everything is documented in Launchpad, and we are discussing it on a weekly basis with a quality of service meeting upstream on IRC. So feel free to join us if you have anything that is interesting for you, or if you have any feedback on the feature, we would love to get it. And I think we're done. Questions? Okay, let me see if I understand. Oh. Yeah, I'll repeat the question. Okay, that's fine. Yeah, so if I understand correctly, the question is there going to be any relationship between the quality of service in networking and the quality of service that we need? You asked about storage, but there is also for any other aspect. So quality of service is like a general term. We did not have any collaboration discussions around it because it's basically the implementation is individual per project. But obviously, one thing that we did discuss is to have the concept of not something that is going to be like an instant type. When you create a virtual machine, you'd be able to associate it with specific SLA, and that would apply to different policies across the different projects. So this is just an initial thought that we had, and it's going to take time until we have different implementations of quality of service that we would kind of tie them all together. I think it's going to take some time. But yeah, that's a valid thing to discuss. Any other questions? Yes.
Any thoughts about adapting the quota? Meaning, I will keep the tenant to certain number of bandwidth, and as we add APMs, I will keep the quota service.
Okay, so the question is, and I'm a bit rephrasing it, is there an option to have a policy that applies, like to aggregate all the quota for the different VMs, and then if I have 10 VMs, then it would be 1/10 per VM, but if I have 100 VM, it would be 100 of the traffic per VM. So yes, we've discussed that. It's more complicated in terms of implementation because we would need to adaptively work on the policies. Obviously, it's a feature. I don't think we have a launchpad for that specific use case, but it would be nice if you can go ahead and report this. It would be obviously something that we can discuss. But it wasn't the first step that we chose to take. Yeah, any other questions? Yes. Bandwidth and packets per second, okay. So you can choose, like I started the first slide, was about the lack of standard in the industry. There's no single way to measure it, and there's no one solution. That's the solution that we chose, and basically what we did is we were basing all the API and the OVS. Well, let me talk specifically on the reference implementation, because you can choose how to implement it. In the reference implementation, we simply chose to leverage whatever we have in OVS. So it was a no-brainer for us. We didn't have an in-depth discussion on it. We were just leveraging whatever was chosen in OVS for us. There is, if you notice the details there, there's a bug in the API. Like there's the max kilobits per second that you can choose, but also you can choose the max, like the burst, how much you can send in one bit. And the burst is marked as kilobits per second, but it's not per second, it's just a typo. But since it's in the API, good luck fixing it in a backwards compatible way. So yeah, we have a launchpad to fix that. It's not really per second, it's just a kilobits, but we need to fix this typo. Hopefully that helps. Yeah, any other questions? Yes. Yes, so that's a really good question. Thank you for asking it. So the question was, how do we actually monitor or get a feedback from the compute node itself about what actually happens? Like we set a specific policy, but how do we know how much consumption we have? So this is something we've been discussing, and actually there is a dedicated project for it. It's not part of the quality of service mechanism because it applies to any features in Neutron, and we know we have a gap there across the features that we need to close. So one of the things, and it got a lot of focus in the Atlanta Summit, is to have a monitoring mechanism in place that would apply across the features, that would give feedback from the compute node on what's going on. For example, we need the same thing on security group, and I think there was another feature that was asking for the same mechanism. So we're working across the features to solve this as a whole thing and not specifically for quality of service. So this is something that the upstream community is working on today. Yes, please. Okay, so the question is, did we measure jitter and latency? So the simple answer is not yet, unfortunately. There are a few reasons for that. There was no agreement how to do it. So we went with the things we could agree on to get something into the code base, and that could be extended. Now it's a matter of resources. Do you want to do it? Are we do we have someone that is interested in doing it? Obviously, the mechanism is extendable, and you can feel free to extend it in any way you think is right, and obviously discuss it with the community beforehand. Yeah. Any more questions? Okay, thank you, guys.